Good evening and welcome everybody, this is Obi-Wan Piz for In Simplex Pachinko. Sorry for music and ads and everything. Didn't work quite as intended. Spotify decided it didn't want to load, so it took a very long time. Anyway, we're here tonight doing more GRE work. So we're going to be looking at, as usual on Wednesdays, cracking the GRE math subject test. This is going to be the section on theorems concerning continuous functions and looking at the definition of derivative. So oh, wait. I wanted to save this. Save. Export image PNG. Close enough. All right. Okay. Get everything all set up now. Took long enough. As interesting as that one is. There's an example in here that's let f be a function where it's going to be 0 if x is an irrational number and 1 over n if x is a rational number m over n in lowest terms. Determine that it's continuous at all irrational numbers. That's nuts. Okay. So for Theora, for continuous functions, first one we're going to talk about is the extreme value theorem. If f is a function that's continuous on a closed interval, A to B. Then F obtains an absolute maximum value. M such that F at C equals M, and C is on that interval A to B. And an absolute minimum. Value N such that F at D is equal to N, and D is also on said interval A to B. Alternatively, there exists C and D inside of our closed interval A to B, such that F at C is less than or equal to F at X is less than or equal to F at D for all X in the interval A to B. So our extreme value theorem is saying that there is going to be an absolute minimum and an absolute maximum somewhere on the closed interval A to B.
Hello there.
It's me. Okay, there are also from analysis, and this is more Zach's alley, but nonetheless, we have Bolzano's theorem. If f is a continuous function on the closed interval I is A to B, same as before, such that f at A and f at B have opposite signs. There exists a C within our closed interval A to B, such that f at c is equal to 0. This is also known as the see, it's in our pre-calc book. It's probably a zeros theorem or something like that. Right, and technically, just this part here does also imply that there can be more than one. Right, there exists some c on that interval a to b, such that f of c is 0. Again, at least 1. And this is generalized to our intermediate value theorem. If f is a continuous function, good evening, everybody, from e to the 2i pi. Hello, Zach. How's it going? E to the 2i raid? Or just e to the raid. That works, too. I hope you all are having a lovely evening, or afternoon, or whatever time zone you might happen to be in. We just started our stream probably, I don't know, 15 minutes ago. Yeah, there it is, 20 minutes ago, because our Spotify decided to be silly again, and then I went the entire, first 10 minutes completely soundless. It's great. But it's working. Can't think as to why it has so many problems. Anyway, we are working currently on the calculus portion of cracking the GRE math subject test, second edition from 2002. It is mostly just a source of problems that we can come up with and be able to explain a whole bunch of stuff at basically all levels between pre-calculus and topology. And once we get up to topology, I'm actually going to be learning some stuff. So, in theory, I could look it up now and all that, but you know. And then we'll do the GRE practice test at the very end of all of this. Now, I will grant you, we are currently on, what, night 15, and we're only that much through the book. So, might be a while. Yep. It's appropriate, right? It could actually, help some stuff. I still maintain that probably something along the lines of tensor calculus would help me a lot, but in terms of that research. But I don't actually know. Okay. Okay. No, that makes sense. Alright. If f is a continuous function on closed interval, I going from a to b, and m is the from the extreme value theorem up above, m is the absolute minimum. Nope. Absolute maximum. And n is the absolute minimum on said interval. Then for every x on said interval, f of x will be between, didn't plan that well, n and m. I think that's how I assigned it up above. Maximum m, minimum n. Yep. Cool. So, for anybody who does not know me already, my name's Obi-Wan Pez. This is N Simplex Pachinko. We do mathy type stuff on Mondays and Wednesdays. Lately, we have been working on Mondays on running through Peter Liljedahl's Building Thinking Classrooms, specifically tailored for math education K through 12. However, I'd used it in community college and had some success. Definitely would need more work. And had several colleagues who had tried it with their classes with, you know, mixed successes. Again, it was everybody's first time trying it for real, so took a little bit of time to get it going. And tonight, again, we were working on cracking the GRE math subject test. If you are doing the graduate record exam, then these streams will be for you. We'll be working our way through the whole book. Again, we are only here after about 15 streams. That's close to 30 hours. We got a long way to go, but hopefully, you know, somebody will get some use out of this eventually, whether that be now or on YouTube. Hi, YouTube. Speaking of which, we also have 2 YouTube channels, one for gaming type stuff and one for mathing type stuff. The gaming channel is at Obi-Wan Pez, and the math content channel is at nsimplexpachinko6542. If you search up nsimplexpachinko on YouTube, you'll find me. Right. So, for tonight, currently working on Calc 1 type stuff, and if you have any questions about any of the Calc 1 stuff, feel free to ask it, especially if I don't cover it. And if you have other questions about anything else, feel free to ask away, because I'll still take time to answer any questions you have. So we'll just take a step away from the specifically GRE stuff, and then work on whatever problems come up. So welcome on in. Hi. And anybody else who's not new, hi again. Welcome back. Okay, so we were setting this up. Then for all x in A to B, that is not where we wanted to go. For all for all y such that n is less than or equal to y is less than or equal to m. Right, for all y values that exist on our particular function, there exists a c on said interval a to b such that f at c is equal to that particular y value that you just picked. If you can't see it, don't worry, we'll draw a picture. So you get some function like this. This is going to be our b comma f at b. This is going to be our a comma f at a. Here, this is going to be our y equals n. And somewhere up here is our y equals m. So this says that no matter what values you pick going across this way, we will always be able to find some value, at least one, such that our x is now on that interval a to b. Or, sorry, c. Let's use the same language. We just found a c for this particular y value that corresponds to that particular function value f of c, which is y. That's not to say that that is the only one. Going the other way, we also note that there are two more solutions for this particular y value. So we could, in fact, come up with a thing that says, hey, by the way, these over here, like this is going to be C1 and this is going to be C2. And maybe this one's going to be C3. So we could come up with whatever C value we wanted. Or not really. We could discover the C values that are appropriate for it and then assign them and say, hey, these are going to work for it. To also note, I also have I also specialize in differential equations. It was kind of one of my favorites. It was also the class where I had the most experience in grad school, and I also used it for a lot of stuff. So we had machine learning. Well, neural networks was another class that I took. Data mining. Not that I remember anything about data mining anymore. And we've used it a bunch. I've also taught differential equations for a number of years at the undergrad level. So we've also done it here on Twitch. So if you also want to see that, most of it is available on YouTube. I think a few of the lectures got eaten by the Great Transfer. We were only allowed to have 100 hours of highlights. So some of it may have gotten eaten. In which case I will attempt to essentially reshoot those particular videos and put them on YouTube when the time comes. Once I get caught up with anything, or everything, because my goodness, there's so much stuff to get caught up with. I was rushing in panic mode, and now that it's not panic mode, gotta motivate myself to actually work. Okay, example. Prove or give a counterexample. If f is continuous on the closed interval 0 to 1, and if 0 is less than or equal to f at x is less than or equal to 1 for every x on 0 to 1, then there exists a point C belonging to 0, 1. It's the domain 0 to 1 for all the x's, such that f of c is equal to c. Right, so this I think is a classic problem used in a proofs class, probably analysis as well, to get students to think about, like, how does continuity work, and in what way could we show that something must be true, or else, again, give a counterexample. This one would be a little bit weird to give a counterexample to, because you'd have to literally prove the disproving proposition. It's not like I could give one single counterexample and be like, oh, look, an exponential function, you know, has values that are down here, therefore it fails. That's not really how it works. You'd have to show that it doesn't work anywhere. Okay, so for this one, what we're going to see is that if f of c equals c, then this is equivalent to y equals x. In functional form, or graphing equation. Right, so if we then graph this, here's 1, and here's 1 as well, give or take, right? Close enough. Then what we should be able to do is find some f such that it goes from x equals 0 to x equals 1 without touching, intersecting, come on, use real words. Without intersecting y equals x. Right? So good luck with that. Mostly because, right, if we have to be able to get from y equals 0, no, x equals 0 to x equals 1 without touching that pink salmon colored line, whatever, right, we note that if we start above y equals x, right, we've got this line over here, we've got this function, and here we're being hemmed in by f of x being equal to 1 along the top. So this is going to essentially run what we call the pigeonhole principle, where, well, not quite. This is more the squeeze theorem. Right, by the squeeze theorem, y equals 1 and y equals x have the same limit as x approaches 1. So the limit as x approaches 1 of 1 is equal to 1. The limit as x approaches 1 of x is also equal to 1. And for all x on 0 to 1, we have that f of x is going to be between x and 1. So therefore, f of x, nope. The limit as x approaches 1 of f of x must be equal to 1. Right? There's the alternative, which is that somewhere down here it's just going to cross the line. And if it crosses the line, then we've already proven that it's going to end up having a value where f of c is equal to c. Because at that particular point, right, our y value, f of c, is going to equal our x value, c. And again, so proven. So again, here we could go like case 1, f of x intersects y equals x for some c. You know what? Let's go the other way. For some c that is strictly between. Nope, strictly between 0 and 1. Then our f of c is going to be equal to c at that particular moment, and again, so proven. Right? 2. We start with a value that is above 0, right? F at 0 is greater than 0, strictly. Then we note that if f of 0 is strictly greater than 0, we're going to force a limit at x equals 1, where our function is going to be equal to 1. And so then we have f of x is equal to 1, and therefore f at 1 is equal to 1. And again, so proven. Version 3, case 3, says we start with our again, y equals x here. We start with a value actually, right? Start with some f at 1 greater than, you know what? Right, strictly between 0 and 1. And you know what? It could be equal to 0 at the bottom as well. Doesn't really matter. It just can't be 1 itself. And realistically, right, we want to do the same thing here. So, f at 0 has to be strictly greater than 0, but it could be less than or equal to 1. Right, then as we trace this back again, it's either going to cross the line, in which case we go back to state 1, or this is going to continue down, and again by the squeeze theorem. The limit as x goes to 0 of x equals 0 equals the limit as x goes to 0 of y equals 0. And we know that our function of x must be either, you know what, we're going to say that it's going to be strictly less than x and greater than or equal to 0 at all times. Technically, by the squeeze theorem, right, if this were equal, then we've already proven what we wanted to prove in the first place, so we don't need to do that. Right, so the limit as x approaches 0 of f of x must be equal to 0 as well. And therefore, f at 0 is equal to 0, so proven. Right, so at some point, there must be a location, f at c, which is equal to c. Hey Rex, how's it going? Talking some Calc 1 tonight. Okay. So this appears to be a slightly ham-fisted way of doing it. The book came up with a much nicer version. Okay. book says. All right, this is what is known as Brewer's fixed point theorem. And this is how we do it. I should write a book, yeah. I mean, I'd like to do a textbook at some point, but like, that's gonna be a long time. So, Brewer's fixed point theorem says that we're going to take the intermediate value theorem, right? If the same thing that I said, if f at 0 equals 0 or f at 1 equals 1, then we're done, right? We don't even need to do anything. If that's true, then QED, we're finished. Alright, so that's like state 1. State 2 is assume that f of x is going to be strictly between for all oh, nope, sorry. That was our f at 0. Again, same deal as I said. It can't be 0 itself, but it can be anything that's less than or equal to 1 and above 0. And 0 is less than or equal to f at 1 is less than 1, strictly. And again, we said this, it was just in different parts. So, Brewer brought it all together at the same time. Go figure. Alright, if we define a new 1 at 0 and 0 everywhere else. So this was demanding that f was continuous. So it was saying that if we have a continuous function on 0 to 1 going across, and if our function values have to be between 0 and 1 going up and down for all x on 0 to 1 going across, then at some point there must be some c value such that our function value is equivalent or is equal to our x value, our input value. It must be true at some point. So the thing that I saw was this means that we must intersect the line y equals x during this graphing somewhere. So then I said, again, assume that it does intersect y equals x at some point, then we get f of c equals c, done. If it is, if f at 0 is between 0 exclusive and 1 inclusive, then we start above, and again, it's either going to cross, so we win, or it's going to go up like that into the corner, and then we can prove by the squeeze theorem that this is going to intersect. And then likewise for below. So Brewer brings it all together and says, let's not, let's not worry about splitting hairs and just say that we know that f of 0 is going to be somewhere over there, and f at 1 is going to be somewhere over there. And then we define, right, g of x equal to f at x minus x. Yeah, we're getting there. if we define g of x as f of x minus x, then g at 0 is going to have a positive value. And g at 1 is going to have a negative value. And now this is just the Bolzano theorem, our intermediate zero theorem. Right, if we have a value at A, which is positive, and B that is negative, or vice versa, then we must have a zero somewhere between A and B. Right, on 0, 1, closed, there must exist a 0. G at C is equal to 0. Which is equal to F at C minus C. Right. I really wish you all wouldn't play that copyrighted music. Alright, anyway. Yeah, so Rex, the mean value theorem doesn't come until after we describe the derivative. So we were saying that in terms of the mean value theorem, that is that the average slope has to be equal to the instantaneous slope at some point. At the moment, we haven't defined either of those things, but we'll get there. Right. Hey, Famished. How's it going? Right. So what we've got here is that, and this is something that Newton worked out, is that if we have a function f of x that is defined at two particular points, so we'll call it a comma f at a, and b comma f at b, he was trying to work out a way in which it was going to become easy to predict motion. The issue in this particular case is that he needed to figure out what the speed of an object was at a particular time. Right, so how do we figure out the speed of an object at one particular moment? So he wasn't actually able to figure out that, at least not immediately, because he knew that if you had the time and positions of an object along its entire path, then what you have is not an instantaneous velocity. What you have is what is better known as an average velocity. So the best he could do initially was to talk about average velocity. So the average velocity of any particular object, as we know, is going to be our distance equals rate times time, or then our rate is equal to distance over time. And that'd be all well and good if we could come up with an instantaneous velocity, but again, just taking distance and time wasn't going to work. We had to calculate what time period is this over, and what was the distance covered during that time period. So here we had our delta f, and here we have our delta t. So let's rewrite that one as f of t rather than f at x. So we went through and said, okay, well, how do we do this? This is actually going to be an average velocity, which is going to be taken by finding the difference in the distance, so our delta f, and then dividing by the change in the amount of time, our delta t. So this is f at b minus f at a all over b minus a. That looks familiar, doesn't it? Right, this is the slope equation that we talk about all through algebra. So we're dealing with the differences in the function values and the differences in the time values. How much do we change in the y direction versus how much do we change in the x direction? dy over dx, delta y over delta x, right? We've done all this stuff. So yeah, this is going to end up being just the same as slope. So the genius of Newton is to take this and say, okay, it didn't work to just take the average velocity because, again, we're just going to get the same stuff. However, what happens if we take this value here and we anchor it? That's totally an anchor. And we take this one and we slide it this way. Such that we end up with a completely new location. Right? We start with a completely new location for b comma f at b. Oops. We say, like, you know, this is the second one we're trying, so b2 f of b2. Put that there now. And then we can keep going b3 f at b3, b4 f at b4, move them closer and closer and closer to that anchored point. Well, that means that we're going to get a closer and closer approximation to the actual instantaneous velocity at that point, a comma f at a. But we're not going to get one that's actually exactly instantaneous, because if we put them literally on top of each other, then there is no change in our x values and no change in our y values. So we end up with 0 over 0, which is an indeterminate form. And we've already dealt with that bit earlier. So we said that, you know, indeterminate forms aren't particularly useful. It's just that now what we can do instead is say, what is the limit as b starts moving toward a of f at b minus f at a over b minus a. All right, that's where we're going to leave it before the break. Everybody get up, stretch, go get water, go cycle your water, go do some exercises, run around the house, whatever it is you're going to do, and meet back in 3 minutes. We shall return. Thank you so much for coming, and yep, see you shortly. And we return. Okay, so we were talking about what happens if we start moving point B comma F at B closer to point A comma F at A, and our delta F and our delta T start becoming smaller and smaller and smaller values and approaching 0 over 0. But at the very least, they become closer and closer and closer to the correct instantaneous slope value at the location A comma F at A. And if you ever want to just verify that for yourself, you can come up with a kind of standard table, and you say, okay, I've got the F at B minus F at A over B minus A. Okay, so if we do something like F at X is equal to square root of X. Oh, we picked one hard. Okay. It's not too bad. But we'll do A equals 4, and B initial is going to be 9. Right, so we do the easy stuff first. We say what's going to happen when we start with 4 and 9, and then we'll keep moving things back further and further and further. Taking the square root, being f of x, is going to get us values of 2 and 3 respectively. And then to say, again, this is B0, B1, B2, and B3. Okay, so we're going to get, this is f of b is 3, f of a is 2, so that's 3 minus 2, over, at the bottom, 9 minus 4. It's going to be equal to 1 over 5, which is equal to 0.2. Okay. If we select instead, B1 is going to be, let's just jump it down to 6. So, much closer value. We do kind of want to get to the point here. So, where did my... Hey, $5. How's it going? They're sitting right on top of the... Yeah, sitting on top of the pile. Right there. Alright, so the square root of 6 is 2.44948 and a bunch of other stuff. If we then go over to our average velocity or average slope in this particular case, then what we get is this number 2.44948, etc., minus 2 all over 6 minus 4, which is going to be a 2 on the bottom, and then a 0.44948 on the top, which is going to be approximately right, minus 2 over 2. Yeah, right. Is a 0.2247448. More stuff beyond that. Okay, now let's move a bit closer. So let's just do like 4.5. Okay, 4.5, you take the square root, we get 2.12132, and again, more stuff after that. So we get 2.12132, etc., minus 2 over 4.5 minus 4. It's going to be a 0.5 at the bottom, and then a 0.12132, etc., up top. The denominator is a half, so we can multiply both top and bottom by 2 in order to knock that stuff out. And then we get... Alright, 0.24264,068. More stuff after that. Okay, and one last one. Let's pick 4.001. For this, we get square root is 2.000249984, and more stuff. Okay, this is going to end up just being I'm going to cut to the chase a little bit here. Minus 2. Okay, is this answer divided by 4.001 minus 4 is just going to get us 0.001. Okay, this is 2.49984 times 10 to the negative fourth. We get that in there. This is going to get us 0.249984377, and again, more stuff. If we get values that are going to be closer and closer and closer to 4 without actually touching 4, then what we're going to notice is that these values will get dangerously close to 0.25, or at least it looks like it. I bet we could probably prove it, not that we're actually going to do it just yet. Well, we will show very soon that is in fact what happens. So now we can do this limit definition. In order to say that this is going to get us this is going to get us the limit as b approaches a of our average slope that'll work of our average slope, which is going to end up getting us a particular value, which we are going to call the derivative at that value a. Right? So the average rate of change becomes our average slope, but as our points get closer and closer and closer together, this ends up becoming our instantaneous slope. At a, which is again also called our derivative at a. Now, there are some rules behind the derivative. You can't just take a derivative everywhere you want. Does have to be a continuous function along a close interval. And also, we could define this instead of defining it at A for some point B that's getting closer and closer and closer to it. What we can do is we could say, you know what? We can define this in terms of the difference between the individual values. So here we just let B be equal to A plus H. So now f at A plus H minus f at A divided by A plus H minus A. We're taking the limit as B, which was A plus H, is approaching A. Well, we can clean this up a little bit. So here we notice that A plus H minus A is just going to be H. And at the bottom here, A plus H is going to be going to A, is equivalent to saying that H is becoming closer and closer to 0. So here, f of A plus H minus f at A all over just H is going to be equal to, again, f prime, the derivative of f at A specifically. And then we can generalize. It didn't have to just be at A. It could be at literally any point that we choose. So instead of f at A or f at A plus H, we say that this is now going to be taking the limit as H goes to 0 of f of x plus H minus f at x over H, as H goes to 0 is going to be equal to f prime at x. Right, whereas this version is the derivative of f as a function of x. So I often actually do this with my pre-calc students. There's even a section on it where we find something called the difference quotient. We say that our function f of x is going to be equal to like x squared minus 2x plus 1. Right? Yeah, that's fine. And we want to find out what is the slope going to be at any particular point? So again, we do this in terms of the original one where we just take 2 points and then try to find the slope between it. Easy enough. We try to find what happens when we take one singular point and some distance away that it goes. And then once we do that, we say, okay, now let's generalize it to say, what happens if we just want any particular point anywhere in the entire function, and then any distance that we want to evaluate as well. So we're saying that we want the average slope. So this is f of x plus h minus f at x all over x plus h minus x, which again is just h. So the average slope between any 2 points could be given by this particular formula. This is going to end up becoming x plus h squared minus 2x, 2 parentheses, x plus h plus 1 all over h, and then minus parentheses on the top, x squared minus 2x plus 1 is equal to x plus h parentheses squared is going to be x squared plus 2xh plus h squared minus 2 times the quantity x plus h is minus 2x minus 2h plus 1 minus x squared plus 2x minus 1. And all of this can be multiplied by 1 over h because I don't want to draw a gigantic bar under the whole thing. Okay, and then we get here that our negative 2x and our positive 2x are going to add to 0, as is our plus 1 and our minus 1. Guess we'll do 2 lines on those. I don't know. And as are the negative x squared and positive x squared. Which then leaves 2xh plus h squared minus 2h all divided by h, which is h parentheses 2x plus h minus 2 all over h. Those divide out very nicely. And so we're left with, let's not do that. M bar is going to be equal to 2x plus h minus 2. So, where do you want to start? That's your x. How far do you want to go? That's your h. If you go in the positive direction, that's positive h. If you go in the negative direction, that's negative h. And our slope can be found, again, as the average slope between the starting point right, x equals 2, and distance is going to be h equals 4, right? So we could do something like this, which then gets us that we have m bar for this setup is going to be that we get 2 times 2 plus 4 minus 2 is going to be 4 plus 4 minus 2 is 8 minus 2 is 6. So this is the m bar for that particular function, the average slope that cuts along these 2 particular points on this function. X is equal to 2, and then h is 4, so x is also equal to 6. Right, so then we end up saying, what if h is 0? Then we get our m star It's going to be equal to 2x minus 2. And very interestingly, right, this is what happens when we take the limit of our f of x plus h minus f of x all over h as h goes to 0. Right? This is the derivative. That's pretty awesome. So the derivative of, again, this was x squared. So if f of x equals x squared minus 2x plus 1, f prime at x was equal to 2x minus 2. So this is something we did, again, like I said, in my pre-calc class. It got them thinking, and we kind of remind them every so often that we could end up using this difference quotient in order to figure out what the, not just what your average slope is going to end up being, but then later on we could say, what is the derivative of this particular function? And then you know, oh, I'm just going to do the difference quotient thing that we were doing earlier, and then h is going to be equal to 0. I know I converted at least one student from being a taking pre-calc, not taking calc, into, wow, I think I'd really like to take calculus. Can't remember what they switched their major to make that happen, but it was like, you know, just using it as a, they used it in changing their program slightly. I don't remember what it was. Ah, well. It's been too many years. But I will say, right, they didn't go into engineering. It was just like, okay. They were just interested in calculus and figured out what that would mean if they took calc. And it did change their major slightly, but they were able to do something cool and keep the majority of their classes the same. Okay, so then what does that mean? Well, now we have a powerful new tool that we can plug in pretty much any function we want and see what's going to happen. Right, so let's continue this by saying, hey, we did f of x equals the square root of x in this last one up here. Let's try to see if we can actually find the derivative, the value of the derivative at 4, and was it 0.25, like I said it should be. So, we take f of x, which in this case is the square root of x. We bring that over and say f prime at x is going to be equal to the limit as h goes to 0 of the square root of x plus h minus the square root of x all over h. Now, you're not actually able to add square roots to each other that have different radicands, so this looks like we're stuck. And like if you just plug in h equals 0, we again end up with that indeterminate value 0 over 0. So that's not going to work. The good news is that you do know, if you've been doing pre-calc, especially if you did pre-calc with me, you do know that there is something you can do here with square root functions in order to like change things up a bit. And that is, we want to rationalize the numerator. How do you rationalize numerators? Well, just like with complex numbers, and just like with any of these weird square root values, we can multiply by the conjugate of this number. In this case, it's going to be the square root of x plus h plus the square root of x divided by itself. And this is going to end up being the limit as h goes to 0 of parentheses x plus h, right? We square our x square root of x plus h, and just the radicand comes out. So here, multiplying the square root of x plus h times itself, square roots go away. Okay, and then we've got the square root of x plus h times the square root of x, and we've also got a negative square root of x times the square root of x plus h. So these terms are the same. One's commuted multiplicatively, and then they have opposite signs as each other. So that's going to sum to 0. Right, so we get a plus root x plus h. And we've also got a minus root x plus h. Combine it any way you want, it doesn't matter, it's all the same stuff. Then we've got the square root of x times the negative square root of x, so that's going to be the negative of now just x. Again, root x times root x, we get a root x squared, it's going to be just x. Okay, and in the denominator we get an h times the quantity, square root of x plus h, plus the square root of x. Now we get the limit as h goes to 0 of x plus h plus 0 for the two middle terms minus x over h times square root of x plus h minus plus the square root of x. Which is equal to limit as h goes to 0 of just the top is just h, the bottom is h times square root of x plus h plus the square root of x. Well, these h's are going to divide out, so we've only got ones, and the only other h that's here is inside of the square root, so we can apply this, and then we just get that 1 over f prime of x is equal to 1 over, here we have the square root of x plus 0 plus the square root of x. So f prime at x is now equal to 1 over twice square root of x. Right, and as a note, right, what was f prime at 4? That was 1 over 2 times the square root of 4. Square root of 4 is 2. So 1 over 2 times 2, 1 over 4. Right, and we were sure from earlier that we should get a square root, or sorry, the square root function should have a slope value at x equals 4 of approximately 0.25. So now we've analytically shown that it is in fact 1/4. Not even just approximately 1/4, it is 1/4. And we showed that generally speaking, the slope at any particular point along our square root function is going to be 1 over twice the square root of that function. So that's just 1 over twice the original function value. Well, that's kind of interesting. Even if it doesn't necessarily do anything, even if we're not really supposed to use, like, right, f prime at x is equal to 1 over twice the original function value f at x. Or, interestingly, right, f at x times its slope is always going to be equal to 1/2. That one's kind of fun. Right. So we did have to watch out for some issues that will crop up, namely something like, what if f of x is equal to the absolute value of x? Right? Then f prime at x asterisk is equal to absolute value x plus h minus absolute value of x all divided by h. Hang on. No, that's true. Okay, we're good. Okay, so what we actually get here, if we look at what do we do when what do we get when we have something like this? Again, this limit. H goes to 0. Right, there's no real way to make this nice, but we can break it up as the definition. So this is going to be the limit as h goes to 0 from the negative side is going to be parentheses, negative parentheses, x plus h minus negative x all over h which is going to be limit as h goes to 0 from the negative side. Here we have negative x minus h plus x all over h. Right, our x's will nicely add out, and then we end up with a negative h over h. Limit h goes to 0 from the negative side is negative h over h, which is equal to negative 1. Not surprising, right? The slope on the negative side of an absolute value function is negative 1, just without it being transformed. And then f prime of x is equal to the limit as h goes to 0 from the positive side. We just have x plus h minus x all over h, which is going to be equal to limit h goes to 0 from the positive side of h over h, which is equal to positive 1. this creates a small problem. Right, asterisk. These numbers don't agree with each other. Ever. Right? We can't get some sort of value. Right, f of x is the absolute value of x. And here we have value that goes off like this in the positive direction, and a value that goes off like this in the negative direction. So yeah, that's a little bit of an issue. Right, and at 0 itself, like, I guess maybe technically we said that by definition, it has a by definition, this follows the positive side at like x equals 0, but the problem here is that it doesn't really work. Right, so we have an issue where, like, if you tried to measure the slope at x equals 0, you've got conflicting answers coming in from both sides. So this is not going to end up being a continuous function. Right, the average slope, the average rate of change doesn't match coming from either side. So this ends up failing for us. Right, if anybody does have any questions, let me know. Otherwise, we'll just keep plowing on through more of the calculus material here. Right, this says that our the values from the left and right, the limits of the slope function, right? The limits of the slope function don't exist. And the thing, this could also happen if we do something like y equals the cube root of x squared. Same deal. So the issue here is that we end up with something that looks like this, very roughly. Okay, same deal. Right, limits of the slope function do not agree, therefore f prime at x, if we define this as f prime. F prime itself is not a continuous function at x equals 0. It's not going to work. Right, same deal. These are called cusps. This occurs anytime that our slope functions don't agree coming in from either side. Okay. Also, want to discuss what happens when you have sums, products, quotients, and is a linear operator. So first off, we use notation, which is a little bit different from other areas of mathematics. It's just a new thing, really. So derivative f prime at x can also be written as, if you remember, we looked at delta f over delta x. This is just going one further and saying that, hey, we took that delta and we made it infinitesimally small. So our deltas become d's, essentially. And we say we're going to do df over dx are going to be the differentials which let us know which function it is that we're looking at and which variable it is that we are operating over. So here we're talking specifically about the function f with all of its wavy stuff in the x direction. We're looking at the instantaneous slope going across this particular function. When you get to multivariate calc, so this is Calc 3 in the States for the most part, we start talking about needing to discuss the derivative of a particular function in relation to which of the three spatial variables are we going to use here. Are we doing x's, are we doing y's, or are we doing z's? And so you have to be able to specifically define, I want to take the derivative of this f function, which is on the variables x and y and z, and only look at that particular rate of change in the y direction, for example. So we need different notation for that. It's a little bit different. We're not dealing with it right now. Although, right, in a few months, I'm sure we'll get to that part. Right, so we use these differentials. This is what's usually known as Leibniz notation. Gottfried Wilhelm Leibniz was a German mathematician back in the 1700s, or 1600s, around the same time as Newton. They were contemporaries. They wrote back and forth a bit. Newton challenged, well, no. They didn't really know much about each other, but Leibniz wrote to the Royal Society and copied Newton in on it and basically said, like, you know, I've got this new thing that I'm working on. Would you care to take a look at it? Newton kind of was like, okay, I did that a while ago. But he never published it because Newton never published anything. And so Leibniz came around. Eventually, it was like, I published this thing. And a bunch of people in Germany were like, this is brilliant. It's amazing. It's wonderful. They got to France, and the people in France were like, hey, we got this thing from England. It's actually really nice, and it works great. It's called the calculus. And, you know, people from Leibniz's camp and people from Newton's camp started to overlap in France, and they got arguments going back and forth about which one's better. England and Germany and everybody else starts getting in on it, and then eventually they're like, all right, we need to decide, like, whose is better and who did this first. So it's written to the Royal Society as something to put on the docket. Leibniz ends up coming to England to sit and listen to the proceedings of the Royal Society, over which is presiding one Sir Isaac Newton as its president. Oh no. The Royal Society as a whole wrote a decision which said that Leibniz should get sole credit for realizing what is known as integral calculus, or we'll do it later, it's doing all the anti-derivatives and things like that. And that Leibniz and Newton should receive joint credit for discovering differential calculus, which is the calculus of the differentials, the calculus. These infinitesimals that are used, df and dx, in Newtonian notation, it typically ends up being either x dots, x primes, etc. And in fact, Newton pretty much exclusively used dots because he was using it in terms of like applications. So he was only ever doing stuff that like had application to his work. He did a lot of work with Edmund Halley of the Comet fame, and pretty much the only things that he ever needed the calculus for were finding distance functions. Their derivatives get you rate of change of position is velocity, and then the rate of change of velocity is acceleration. That was pretty much all he needed. And so he went to two derivatives, and that was pretty much it. So you had x as a function, x of t. You had the function x dot of t, which was the velocity. And you had x double dot of t, which is the acceleration. And that was it. Why would you need more dots? So therefore, why do you need further notation? Leibniz, on the other hand, realized that this could be extended further. And he said, this is going to need, like if we do second derivative, if we do third derivative, if we then do fourth derivative, like do I put 4 hashes there? That's going to be really hard. So what he decided to do was to start putting Roman numerals, 4, 5, 6, etc. He was thinking about what to do when we extend this eventually, because he was a theorist and he was a teacher. And realistically, he was trying to get his students to understand his concepts. So it was much easier to get them to understand things if you have a much more rigorous and, quite frankly, useful system that's going to be able to tell people what it is that you're doing.
Listen to Renee Rapp's complete collection on Spotify.
Right, so the Newtonian notation again was basically like, we're going to do x dot and x double dot, and then like something to the effect of, why would you need more? This has no use. And naturally, we know it these days as, well, yes, there is a use. You might not see it, but... Okay. So is this a linear operator? So if it is a linear operator, then what should happen is this is all of this is going to be closed under a linear combination. So if we end up doing right, f plus g prime of x should be equal to f prime at x plus g prime at x, and we'll throw a minus in there just cuz. Also, k times f of x, k times f prime at x should be equal to, and again, question mark for now, should be equal to k times f prime at x. So under a linear combination, what we're saying is that as long as both of these individual properties hold, then this should work for all derivatives, and derivatives as a whole should be linear operators. So can we do a linear combination? Can we add and subtract stuff? And can we multiply them by constants? And still get the same thing. Right, so if we do f plus or minus g, right, f plus or minus g prime at x should be parentheses f of x plus h plus minus g of x plus h minus parentheses f of x plus h plus minus, no, that's just x, f at x plus minus g at x, all over h, and again this should be limited. So we're going to take the limit as h goes to 0 of that whole thing. So if this holds, then we can add and subtract our derivatives and have no problem. So this is going to be equal to limit h goes to 0 of, separate these things. This is f at x plus h minus f at x plus minus g at x plus h minus plus, because the sign is switched, g at x. And we could split these. Okay, really, I should isolate that plus minus to make sure it doesn't get too terribly confusing. Plus in between here. Okay, this is equal to, well, the first one, limit as h approaches 0 of f of x plus h minus f of x over h. That is the derivative of f. All right, f plus or minus g parentheses, all primed of x is equal to f prime at x. Right, and then if I take out, if I factor out the plus minus, then what happens is our g of x plus h is just plus g of x plus h, and then the minus plus g of x becomes now minus g of x over h. And now this is just going to be plus g prime at x. Hey, it worked. We're going to snooze that ad. I think we're going to call it after this. Linear operator proof. Okay, so this is number 1. Oops. Plus or minus. Right, works for both. And then, if we have k times f, parentheses prime of x, we now have this as the limit, as h approaches 0, of k times h of x plus h minus k times f of x all over h. Okay, factor a k from the top. H goes to 0 of k times f of x plus h minus f at x all over h. And that limit as h approaches 0 does not affect k. So k just kicks to the outside, and then we're left with the limit as h approaches 0 of f of x plus h minus f of x all over h, which is now k times f prime of x. So k times f parentheses prime of x is equal to that. So we do get by using these two properties together. Nope. Right, derivatives are linear operators. So that's pretty cool. Our derivatives are going to be closed under linear combinations. So you could just decide to, again, add and subtract any other functions, or add and subtract them in any constant multiple combination, and you get the same derivative regardless of how you actually do that. Right, so could do, again, k, let's just do k0 with f0 at x plus k1 f1 at x plus ... all the way out to however many k's, k sub n, f sub n of x plus ... You can keep going on forever. Parentheses, take the derivative of it, and let's do the other derivative. dx is going to be equal to k sub 0 times df0 dx plus k1 times df1 dx plus ... all the way out to k sub n times df sub n over dx plus ... Right? It's all the same stuff. Hey Phobos, how's it going? Right? So we could do this in any way, any combination you want, any linear combination. We can do them as a whole, take the derivative of the whole thing, or we can take them as take the derivative of each individual thing, and we get the exact same thing either way we do it. So this is why doing these derivatives with these really simple rules are really cool, really easy, really nice, and we could figure out some more complicated stuff next time. So we are, like I said, going to call it there, but exhausted, but trying to read some material for studies and paint a picture. Ooh. And clean your house. Yeah, that's a tough one. Let's see. I think we are going to go see Rhacodactylus, who is doing Who Believes Misinformation? Science and Technology. So we will be back possibly tomorrow for playing games, but definitely Friday for Against the Storm. And then again on hopefully Sunday for Satisfactory Sunday. And then again on Monday, Wednesday for mathy type stuff. Monday again, we'll be going over Building Thinking Classrooms by Peter Liljedahl. And the next chapter is where are students going to work in the thinking classrooms, and what are the what is the theory behind it, and what are some of the evidences that popped up throughout the study. And then on Wednesday again, we'll be working our way through cracking the GRE math test, as always, starting with those property rules that we were talking about. So what about product, quotient, a chain rule, and doing an inverse function? So those are going to be the starters for next time, and then we'll move on from there. So I hope you all have a lovely rest of your week, and I will see you again definitely on Friday, maybe tomorrow, depending on how things are going. So thanks so much, Phobos. Thanks so much, everybody, for coming, and I'll see you next time. This is Obi-Wan Pez for N Simplex Pachinko. Have a good night.